first two lessons were on solving trig equations, and then the next few lessons were all on identities. Now we're going to be looking at equations, subbing identities into them to then solve them. Okay? One thing you want to do when you're solving equations is, first of all, you have to realize it's an equation, not an identity. So with equations, we can move from left-hand side to right-hand side. Whereas identities, you have to prove that the left-hand side equals the right-hand side. Okay, so we have a little more freedom that we can move things from side to side. One thing that's important is you want to simplify each equation so that you're in terms of your primary trig ratios, so sine, cosine, and tan. For the first example, I'll just show you how that's done. You're going to need all the room for A, so don't worry about B, okay? So we're starting off with 2 cosine x squared plus 3 sine x equals 0. Can you guys think of any way that you could factor in or break it down to isolate just sine x equals 0 or cosine x equals something? Is there any way? Just looking at it?
You could subtract 2 cos x squared.
Okay, but then we have a trig ratio equals a trig ratio. So now we have to use our knowledge of identities and replace a portion of this equation with an identity. So if we have 3 sine x and cosine x squared, I'm going to get a little creative with that cosine x squared, and I want it to just be in terms of sine. So can you guys take a look on your formula sheet, find the Pythagorean identities, and tell me how we could get creative with the Pythagorean identities so that it's in terms of sine.
1 minus sine squared.
Perfect. Okay, so one of the identities is cosine x squared plus sine x squared equals 1. So if we want to isolate cosine x squared, we have to move that sine x squared to the right-hand side. So we get 1 minus sine x squared. Okay, perfect. And the whole reason why we're going to be doing that is so that we can eventually factor this equation. So we're going to replace cosine x squared with 1 minus sine x squared, which gives us 2 times 1 minus sine x squared plus 3 sine x all equals 0. Okay, so as everyone's seen, we've replaced cosine x squared using the Pythagorean identity, now with 1 minus sine x squared. Are you okay there? Okay, now let's expand. So multiply 2 into both terms. We get 2 minus 2 sine x squared plus 3 sine x equals 0. And what we have is a second degree trig equation. And when we're solving second degree trig equations, it's easier if we just let sine x equal a variable. So let's let sine x equal a. And if we do that, we get 2 minus 2a squared plus 3a equals 0. And for me personally, when I'm factoring, I like to have a positive a squared. So I'm going to move everything to the right-hand side, giving me 0 equals positive 2a squared minus 3a minus 2. So I've just flipped the signs of each term. Alright, so now we need to factor. And to do that, we've got to figure out what our AC is and our B is, and two numbers that multiply and add to those numbers. So our A times C is 2 times negative 2, which is negative 4, and our B value is negative 3. Okay, so we're going to use negative 4 and positive 1 to break up that middle term, and hence factor by decomposition. Okay, so 0 equals 2a squared. And rather than writing negative 3a, we're going to break it up into negative 4a, positive 1a. So we rewrite the first term, rewrite the last term. It's the middle term that's broken up into 2 terms. Then we can factor by grouping. From the first group, we can take out a 2a. and we are left with a minus 2. And in the second group, we don't factor anything out. We have a common binomial of a minus 2, so let's factor a minus 2 out. And we're now left with 2a plus 1. If this was just a quadratic equation and we were to solve now, we would just look at the binomials, and a would equal positive 2 from the first one, and a would equal negative 1/2 from the second binomial. But what do we have to remember? What was a? Yeah, a was equal to sine x. So we just have to replace sine x back in for our a's. Okay, so we have sine x equals 2, and sine x equals negative 1/2. When you're asked to solve an equation, this is not your final answer. They're basically asking for what values of x could we plug in here to satisfy it so this equation equals 0. Okay, so we're solving for x. And that's within the specific domain 0 to 2 pi. So let's take a look at sine x equals 2 to start. If we were to explore the graph of sine, starts at the origin, waves up, waves down, and cycles back to the x-axis. The maximum is at 1, the minimum is at negative 1. So if we were saying that sine x excuse me, equals 2, they're saying, okay, at 2, is there a value on the graph of sine x? No, it does not exist. Okay, so any value of sine x, if it's greater than 1 or smaller than negative 1, it will not exist. So there's no solution. Okay, and if you went second sine 2, your calculator wouldn't calculate it. Okay, I'll just show you guys. So if I go second sine and I put in the value 2, I'm going to get an error. Okay, and that's because it doesn't fit on the sine graph. It's above its maximum. Okay, so let's see with the second statement if we can find some solutions. So sine x equals negative 1/2. We've got to remember our cast rule to figure out what quadrants the solutions will exist in. Our ratio is negative, so sine will be negative in quadrants 3, and 4. Now we got to figure out our reference angle. Okay, and one easy quick way would be you go second sine 1/2. And just referring back to our special triangles, you could also remember that for 30 degrees, the y-coordinate is 1/2. Okay? So reference angle is 30 degrees.
Why do you have to find a reference angle if it's a graph?
If it's a which, sorry?
Like, because for 2 we did the graph, but then I'm kind of confused for like the negative 1/2.
Okay, so ignore the graph for a second. That was just a visual. If you were to find use your cast rule, okay, it's positive, so sine would occur here and here. But to find your reference angle, you would have to go second sine 2, and this is where we get the error. And I just wanted to show you visually the reason why we have that error is because sine, as it waves, it has a maximum at 1. It doesn't occur at 2. There's an error.
So
it's not on the graph.
You're checking, when you get to the 2 answers, you have to check by if it has a reference angle or not?
This is just going back to when we were solving for x. Like, what are the solutions within the domain 0 to 2 pi? Okay, well that would be all 4 quadrants. And we're trying to figure out what are the values of x that will satisfy this equation.
Yeah.
Okay,
But
maybe
that's just the way you test it every time.
this is how you'd solve every time. Yeah. Okay, so just a reminder from last unit, first you got to go through your cast rule to figure out, okay, what quadrants will your solutions exist in? Sine is negative, so we exist in quadrants 3 and 4. Okay, then we have to figure out the reference angle that we're going to apply in quadrant 3 and apply in quadrant 4.
Okay.
So we haven't quite found our solution yet, we've only found our reference angle.
Okay.
Okay,
Thanks.
no problem. So for quadrant 3, okay, we're going to go 180 plus 30 degrees. So we get 210 degrees as a solution. And for quadrant 4, we're going to go 360 minus 30, and that gives us 330 degrees. So the solutions that we have found are 210 degrees and 330 degrees. So if you were ever asked to solve the following equation, it's basically saying what values of x satisfy this equation. X equals, what did we get? 210 degrees and 330 degrees. Now the domain is in radians, so how should I give my answer? In radians. Okay, so just a reminder, to go from degrees to radians, we have to multiply each by by pi over 180. So when you go 210 divided by 180, what do you guys get?
Not.
I think you're right. Yeah.
Times pi or not times pi?
Well, we're just going to leave the pi as pi. Don't include it in your calculation.
I got 1.17.
Just ignore that pi. 210 divided by 180?
1.17.
Okay, math enter. You should get 7 pi over 6.
Same thing.
So in exact form, it's 7 pi over 6. In decimal form, Emily, you got it.
1.17.
Radians. Awesome. Okay, now we'll calculate 330 divided by 180. 11 pi over 6. Very good. Okay, so our solutions are 7 pi over 6 and 11 pi over 6 within the domain 0 to 2 pi. So I just want a recap of this question just so we can review what has been done. First of all, we applied an identity to make our equation manipulative, or basically to make our equation, how do I word this without mumbling my words? Basically we want to factor, so we have to figure out which identity can we sub in so that we can factor this. Okay, and we figured out that we could replace cosine x squared with the Pythagorean identity. From there we factored it down, and this is where we've isolated our primary trig ratio of sine. Okay, from these primary trig ratios, we then have to figure out what are the solutions, so that it equals 2 or that it equals -1/2. And we got our solution 7 pi over 6 and 11 pi over 6. So the extension to this lesson compared to lesson 1 and 2 in this unit is now just this step. We've got to plug in an identity to get to the factoring. Okay? So I'm going to see if you guys can help me out finding the identity for the next one. We have 4 minus 7 sine x equals cosine 2x. Okay, which of the 3 identities for cosine 2x, so we have a double angle, would be the most efficient in solving this equation? So in other words, on the right-hand side of the equation, what could I replace cos 2x with so that I could eventually factor this?
1 minus 2 sin.
Good. Okay. So I'll just point out where your double angles are. Make sure everyone's looking. You got to get familiar with this formula sheet. So your double angles are just on the bottom section of your trig identities. Cosine 2a, you'll notice there's 1, 2, 3 trig identities. So we've got to figure out, if I have a sine x on one side, let's try and get everything in terms of sine. And the only trig identity for the double angle of cosine that has sine in it would be the last one, 1 minus 2 sine a squared. Okay, all the other ones have cosine or cosine and sine. So if the left-hand side has sine, let's try and make everything in terms of sine. So the double angle identity we'll use is cosine 2x equals 1 minus 2 sine x squared. That's what we're going to replace on the right-hand side of our equation. I copied that. No, we got it right. So now we can start to solve. We have 4 minus 7 sine x equals, instead of cosine 2x, we're now going to write 1 minus 2 sine x squared. The goal is we want to factor this. So just like quadratic equations, we have to set it equal to 0. So I'm going to move everything to the left-hand side. Okay, and I get 2 sine x squared minus 7 sine x. 4 minus 1 is positive 3. That equals 0. So I've added 2 sine x squared to the left-hand side, and I've subtracted 1 from 4. Now some of you might be able to factor right away just using sine x, but most of you will probably like the substitution, so I'll just go ahead and do that. Let a equal sine x. So now we have 2a squared minus 7a plus 3 equals 0. Then we have to factor. Okay, AC is equal to 6, 2 times 3, and our B is equal to negative 7. So the two numbers we'll use to break up the middle term will be negative 6 and negative 1. So we get 2a squared minus 6a minus 1a plus 3 equals 0. Now factor by grouping. Boom, boom. Take out the common factors from each group. We get 2a multiplied by a minus 3. Factor the negative 1 of the second group, and we get, again, a minus 3. Both groups have a common factor of a minus 3, so let's factor that out. And we're left with 2a minus 1 equals 0. So from here, a equals 3, and a equals 1/2. Okay, for a equals 3, a is not actually a, it's actually sine x. Will sine x ever equal 3? No, because its maximum's at 1, so anything above 1 will not be valid. If you want to check that, go second sine 3, you'll get an error. It's not going to work. Okay, so this does not exist, no solution. But for sine equals 1/2, we're just going to replace a with sine. And we can solve for the values of x, that would give us a ratio of 1/2. So our casserole puts us in what quadrants? Okay, good. Ratio is positive, solutions will occur in quadrants 1 and 2. Then we have to find our reference angle. And we did this in the last example, but if you want, just go second sine 1/2 and you'll get 30 degrees. So our solutions will be x equals, in quadrant 1, 30, and in quadrant 2, 150. Okay, it doesn't tell us the domain, so we could just, oh, that's why, because it's asking for the general solution. Okay, so be careful if it's asking for general solution, that's assuming that this equation is going to keep going and going and going forever. Okay, if we were to write this in terms of degrees, we could just say that the general solution x would be equal to 30 degrees plus, what's the period of sine? 2 pi. So 360 degrees times n. And then for 150, we'd have 150 degrees plus another period 360 degrees times n, where n is an integer. So just a reminder, when we're finding general solutions, if we had the graph of sine, and we're looking for the solutions when it equals a half, that means we have solutions here every time we intersect with the line 1/2. Those are solutions. So within the first period, from here to here, we only have 2 solutions, and that was 30 and 150. Okay, but if we go to the next period, we'd have to add 360, add 360, and we just keep doing that. Okay, I didn't graph the correct graph, but I was just showing you a sign. Okay. So algebraically, we've seen how we can sub in identities to then factor, and then simplify to find our solutions. Okay, sometimes you might want to get creative when you're solving algebraically, and you might want to divide by a cosine or a sine. And specifically in this example, we're going to look at if that is actually possible. Okay? And there's one example where we are allowed to do it, one example where we're not. So we have 2 trig equations. First one is sine x equals cosine x, and the second one is sine 2x equals cosine x. Okay, and we're looking at the domain between 0 and 2 pi. So a student tried to attempt to solve this, starting with just the first one, sine x equals cosine x. What they decided to do is divide both sides by cosine, thinking that if they do that, this side will equal 1. And what is the identity for sine over cosine? Tan. Okay, so these cosines cancel out, we get 1, and sine over cosine is tan. Which means we can then solve using our cast rule and our reference angle. So tan has a positive ratio, that means we'll have solutions in quadrants 1 and 3. The reference angle, you can think about your special triangles, or you can just go second tan 1. You'll get, excuse me, you'll get 45 degrees. So if our reference angle is 45 degrees in quadrant 1, we have a solution of 45 degrees. And it's quadrant 3, it's 180 plus 45, so we get 225 degrees. The domain's in radians, so we also have to put our answers in radians. So 45 as a radian is pi over 4. And I'll let you guys check what's the radian for 225. Divide it by 180. Is it 7 pi over 4?
Yeah.
Yeah?
Yeah.
Did you check it?
No.
No, but you think.
225 over 180?
Oh, just kidding.
5
It's
over 4,
5 pi
Chris.
over
5 pi
4.
over 4?
I
Okay.
thought it was.
Sure was going to be missing.
I don't think the other class corrected me then. I like that you guys are willing to, actually test it. It's good. Except for Chris.
I trust you. I trust you.
Okay, so we have pi over 4 and 5 pi over 4. And I'll just show you a visual of that. So looking at the graph below, we have the graph of sine, as you can see here, and the graph of cosine. When they intersect, we have our solutions. This is one solution, and this is another. That is occurring at 45 degrees, or pi over 4, and 225 degrees, or 5 pi over 4. So on the graph, we have solutions pi over 4 and 5 pi over 4. Just below that, it's asking for what x equals, so you can just plug that in. So in conclusion, the intersection points are solutions. We algebraically solve for 2, graphically we see 2. Now let's check out the next one because we're not going to get those same results. We started with sine 2x equals cosine x. They got a bit creative. Use the double angle identity for sine. And you can check it out in your formula sheet just to verify. Sine 2x is equal to 2 sine x cosine x. So we've just replaced these. Now thinking about getting the right-hand side equal to a value, not a trig ratio, they decided, well, let's try and divide both sides by cosine. Okay, that works. Cos divided by cos is 1, and these cosines will cancel out, so we're left with 2 sine x equals 1. If we isolate that trig ratio, then we then get sine x equals 1/2, which we can then solve for the x solutions. Sine is positive, solutions will be in 1 and 2. Our reference angle, we've done this one a few times, but you're just going to go second sine 1/2. You should get 30 degrees. So if I apply 30 degrees in the first quadrant, I have a solution of 30 degrees. If I apply 30 degrees in the second quadrant, I get 150 degrees. Okay, and in radians, we get pi over 6, and just double check this. 150 divided by 180, 5 pi over 6. Alright, so algebraically we found 2 solutions, but let's look at the graph. Solutions are defined by the intersection points. We have 1, 2, 3, 4. So we have a discrepancy. And the reason is, sometimes we are allowed to divide by cosine x, other times we are not. And we're just going to explore when we can and when we can't in the next explanation. Okay, if you were to graph sine 2x equals cosine x, you could find the intersection points. Do you guys want to try that? Maybe we'll just find it in degree mode to start. Window settings are provided. I'm just going to use the degree measurements instead. So we're going from 0 to 360. Spaced out by pi over 6, or 30 degrees. And we're going from -2 to 2 with a scale of 1. So y1 will be sine 2x and y2 will be cosine x. And then we can just graph them. What are you asking for? Window settings?
Oh, no, sorry. I got that, thanks.
Okay.
That has to be in radian mode, right?
Depends. If your window settings are in radians, then be in radian mode. I put my window settings in degree.
And you put the window settings in degree?
So what mode are you?
Right now I'm in radian.
Okay, so if you're in radian mode, then you want your window settings to also be in radian.
Okay.
Otherwise, it's not going to work.
We're
So-
just doing the second one, right?
Yeah, just the second one.
Like, this. I got it.
So if you already have your graph up, you can start calculating what are the intersection points. We're going to go second trace, number 5. Okay, now, because we've already solved for 30 and 150, let's just take a look. Okay, that's 30 degrees. If I move my cursor close, this one's 150 degrees. So we already know those ones. We need to solve for this one and this one. Okay, so here and here. So keep moving till you get to that one. So 90 degrees. And then we just have to solve for the last one. Okay, so we have 4 solutions: 30 degrees, 90 degrees, 150 degrees, 220 degrees. So underneath the graph, let's just record all those solutions. So in radians, 30 degrees will be pi over 6. Okay, 90 degrees is pi over 2. 150 is 5 pi over 6. And 270 is 3 pi over 2. 4 solutions. So graphically, that's how you could find the solutions. Whereas on the first page, we looked at algebraically how to solve. Now, what if you were given the image on your diploma test and you had to figure out the solutions by looking? You'd want to pay attention to these window settings. What is the scale on the x-axis? Pi over 6. Okay, so that means each little tick is going up by pi over 6, or 30 degrees. Okay, so if this is 30 degrees, then we've added another 60 degrees, so that's 90 degrees. We would just keep adding 30 degrees until we get to our other solutions. Okay, so plus 30, plus 30, plus 30, plus 30, puts us at 270. Okay, so just make sure you're aware of the scale if you ever have to look at a solution from a graph. So just going back to our algebraic work, from the first example, we found 2 solutions, and the graph showed us 2 solutions. From the second example, we found 2 solutions, but the graph showed us 4 solutions. So moving to the next little bit, would you say for part C, does the algebraic solution agree with the graphical solution for the first graph?
Yeah.
Yes. Okay, but it does not agree for the second graph. No. The algebraic solution is correct for the first graph, but it's not in the second graph, and that's because we had a different number of solutions. And the reason why is because we have to think about under what circumstances can we not divide by cosine x. Okay, we looked at this in the restrictions lesson. So when can we not divide by cosine x? When cosine x is equal to 0. In other words, we can't divide by cosine x equals 0. Okay, because we're not allowed to divide by 0. So how do we know when we can divide by cosine x, when we can't? Well, there's a few rules. Okay, and I'm gonna just show you guys the graph of cosine x when it equals 0. So here's cosine. When y equals 0, we have x-intercepts. On cosine x, we have x-intercepts at pi over 2 and 3 pi over 2, which is 90 degrees and 270 degrees. So whenever we have cosine x, where x is equal to 90 or 270, or multiples of that, okay, it's going to equal to 0, and we can't divide by that. So we're never allowed to divide by 0. So to figure out if it is possible or not, what you're going to do is just sub in the value of, for example, 90 degrees, because that's one situation where cosine would equal 0. Okay, let's try that in the first equation and see which case we get. There's 2 cases. So if x equals 90 degrees, and it is a solution to either equation, then the step in which the student divides by cosine x is not valid because she is dividing by 0. Okay, and if x equals 90 degrees is not a solution to either equation, then the step in which the student divides by cosine x is valid because she is dividing by non-zero value. So this situation is saying when we sub in the value, left-hand side will not equal right-hand side. And that means it is valid. We can divide by cosine x. But the first point, if left-hand side is equal to right-hand side, that means we can't divide by cosine x. Okay, so that's how you test it. You just figure out what value of x would be equal to 0. And one example is 90 degrees. You plug that into the left-hand side, plug it into the right-hand side, and see what result we get. So let's try the first graph. Okay, sine 90 degrees equals cosine 90 degrees. If I just draw a picture, you could just put it in your calculator, sine 90, see what you get. Okay, at 90 degrees, we have the ordered pair 0, 1. Sine 90 is always the y-coordinate, it equals 1. Or you could just go sine 90, it equals 1. Okay, cosine 90 is the x-coordinate, so it'll equal 0. Do they equal each other? No. Therefore, we can divide by cosine x. We can.
But if you said it equals 0.
Pardon?
Oh, no.
So this is just a little test to figure out if we can divide by cosine x or not. And the rule is if left-hand side does not equal right-hand side, we can divide by cosine x.
Oh.
Okay? And the flip side, if left-hand side does equal right-hand side, we can't divide by cosine x. So let's try it for sine 2x equals cosine x. Sine 2 times pi over 2 equals cosine pi over 2. On the left-hand side, the pi's, or the 2's will cancel out. And if you just think about sine 180, that's one of the x-intercepts, it'll equal 0. But you can just plug in your calculator, sine 180, you'll get 0. Cosine 90, also equal to 0. So left-hand side equals right-hand side, which means we can't divide by 0. So if we can't divide by cosine x, how are we going to find all 4 solutions? Well, we have to be a little bit more creative in how we're going to solve it. So sine 2x equals cosine x. Rather than dividing by cosine x, we're going to do something else. First, let's take our double angle identity for sine 2x, and we get 2 sine x cosine x equals cosine x. Okay, then subtract cosine to the left-hand side. So rather than dividing, we're just subtracting. And now we can factor. So factor out the cosine x from both terms, and we get cosine x times 2 sine x minus 1 equals 0. And now we can derive our solutions. So from the first term, cosine x, we get cosine x equals 0. And from the second binomial, we get sine x equals 1/2. Okay, so for cosine x equals 0, We've already looked at the solutions. It's going to be pi over 2 and 3 pi over 2 within the 2 pi period. But if you're unsure of that, you can again look at your cast rule. 0 will be positive and negative, so it's all 4 quadrants. To find your reference angle, you're going to go second cosine, 0, and you get 0 degrees. Quadrant 1, wait, 90 degrees. Okay, always double check it. Second cosine 0 is 90 degrees, so in quadrant 1, 0 plus 90 is 90. 180 minus 90 is 90. So we have solutions at 90 degrees. In quadrant 3, 180 plus 90 is 270. And in quadrant 4, 360 minus 90 is also 270. So we have solutions pi over 2 and 3 pi over 2. And that's all from cosine x equals 0. But there's another little part, sine x equals 1/2. Okay, so first look at your cast rules, C-A-S-T. Sine's going to occur in quadrants 1 and 2. We figured out this reference angle a few times. So second sine 1/2, we get 30 degrees. And our solutions will be 30 and 150. So solutions in radians will be pi over 6 and 5 pi over 6, is it? Or 150?
Yeah.
So these are 4 solutions here. Okay? We have pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. You just saying that?
I think I remember from the last one, it's 5 pi over 6.
Yes, it is. Good. All right. So just keep in mind you can divide by a primary trig ratio sometimes, but you have to do a check. Okay, if left-hand side equals right-hand side, we cannot divide by that trig ratio. So last little bit here, we're going to solve equations using double angle identities. And the first little bit, we're just going to look graphically at our solutions. Alright, so the diagram shows f of x and g of x across the domain 0 to 2 pi. For part A, we need to write an equation which has a solution provided by the x-intercepts of the graphs. So that means that all of these are solutions, are x-intercepts. And in total, there's 8. So we're going to have 8 solutions graphically. And if we solve this algebraically, which we're going to do on the next page, we're going to be looking for 8 solutions as well. There's a lot. Okay, now the equation to solve for this would basically be f of x times g of x equals 0. We need y to equal 0, and the only way to get that is if we multiply the two functions. For example, if you were to subtract f of x minus g of x, would you necessarily end up on the x-axis? No. So we have to multiply them. Okay, now let's look at it from another perspective. What if we were asked to find the solutions provided by the x-coordinates of the intersection points? Then we would only have 1 and 2 solutions. And to achieve that, for an intersection, we need f of x equal to g of x. And another way to write an intersection, if we rearrange this, would be f of x minus g of x equals 0. So keeping that in mind, they're now giving us the equations for f of x and g of x. Use a graphing calculator to determine the exact roots of the equation. In this case, they're just doing the equation f of x minus g of x equals 0. Okay, so they've replaced f of x here, here, and then we subtracted that over. Maybe I'll do that underneath. So f of x was 3 sine x squared minus 2. G of x was negative cosine 2x equals 0. If you rearrange, you get what's written here. Okay? Now graphically, rather than putting this into our calculator and solving, let's just go back up to the graph and we can figure out our solutions by looking at it. Okay, one more time. They're going to be here, 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 and here. Now obviously, I don't really have a scale, so I can't find the exact solutions, but I know there's 8. Okay? So let's solve this algebraically and see if we get 8. Okay, I'm just saving a bit of time rather than finding them graphically too. If this was your diploma though, what would be the most efficient way? Algebraic or graphically? Graphing, for sure. Okay, so let's look at part 1. We have 3 sine x squared plus cosine 2x minus 2 equals 0. Okay, what could we apply to make this a little bit easier so that we can actually calculate the solutions? Could I use an identity? Which identity? Maybe one for cosine 2x. So look at your formula sheet. There's a double angle identity. You want to pick the one that just has sine in it. And that one is 1 minus 2 sine x squared. So let's plug that in. We have 3 sine x squared plus 1 minus 2 sine x squared minus 2 equals 0. Combine like terms. We have 3 sine x squared minus 2 sine x squared. So now we have 1 sine x squared. Okay, and 1 minus 2 is negative 1. Always when you're solving, you want to isolate that trig ratio. So let's add the 1 over. We get sine x squared equals 1. Okay, and to get sine x by itself, we need to take the square root. And just remember, when you take the square root, positive, negative. So now we have sine x equals plus or minus 1. So applying the casserole, we can see that we'll have 4 solutions in quadrants 1, 2, 3, and 4. Check out the reference angle now. Okay, second sine 1. What do you guys get? 90? You should get 90 degrees. So if I apply 90 degrees in quadrant 1, I get 90 degrees. In quadrant 2, I get 90 degrees. Quadrant 3, 240 degrees, and quadrant 4, 240 degrees. So my solutions for x are 90 degrees and 270. Okay, so I just solved the intersection. F of x equals g of x. And as you saw in the graph, there's only 2 solutions. Now let's solve for part 2. Okay, so part 2 was f of x times g of x equals 0. And here we have, what was this one again? F of x? And that's g of x. Okay, so they're just multiplied by each other. So we don't actually have to manipulate this one. We can just go right from the factors and then solve. So negative cosine 2x equals 0. If I divide by that negative, I just get cosine 2x equals 0. Or switch it to the other side. You get cosine 2x equals 0. And then from this one, we get sine x squared equals positive 2 over 3. Isolating just the sign, I have to take the square root of both sides, and remember to take the positive and negative square root. So
Junior
sine
fractions.
x will equal plus or minus square root 2 over 3. So we need to find solutions from this trig ratio and this trig ratio. And this one is unique. We've got to go back to our double angle solutions. Do you remember how we had to extend the domain instead of cosine being over domain 0 to 2 pi? We had to stretch it out to 4 pi. Do you remember that? It was a while ago. First, what we need to do is figure out what are the solutions between 0 and 2 pi. And then if we were to extend that to 4 pi, we would have twice the amount of solutions. Okay? Because what does the stretch factor do? Is it multiplying by 2? Is it a horizontal stretch by 2 or a half? Half. So how many solutions? Like if this is regularly cosine from 0 to 2 pi, if this graph is compressed by 1/2, by a factor of half, how many solutions rather than 2 will we have? 4. Because now all of a sudden it's going to be like this. Okay, so we have 1, 2, 3, 4 solutions. So we have to be aware that double angles also compress or stretch. So let's first figure out what is cosine x equals 0. Well, in all 4 quadrants, we would have a reference angle of second cosine 0. What do we get there? Second cosine 0? 90. Yeah. Okay, so if I apply 90 degrees in all 4 quadrants, my solutions are 90 degrees and 270 degrees. Okay, but we have to remember that this was actually for cosine 2x. So if I put 2x equals that, I also need to stretch out all the way to the domain 0 to 4 pi. So looking at the period of cosine, we have 2 pi or 360, so 90 plus 360. My math's terrible right now. What do we get?
450.
Thank you. 450 degrees, and then 270 plus 360, we get 630. So those are the solutions stretched over 0 to 4 pi. We need the solutions just from 0 to 2 pi. So what can I do with that too? Divide everything by 2. Okay, so x will then equal, okay, if we divide this by 2, divide by 2, divide by 2. Okay, I'll get 45 degrees, and then 135, and then 225, and 315. So those are my solutions from cosine 2x equals 0. We'll convert our answers to radians after. Now we have to figure out our solutions from sine x equals plus or minus square root of 2 over 3. Do you guys care if I erase this? Okay. Just want to keep all my work in the screen so those at home can see it too. Okay, so we have sine x equals plus or minus square root of 2 over 3. So first of all, we know we're going to have solutions in all 4 quadrants because we have a positive and a negative. then we're gonna find our reference angle. So x will equal second sine the square root of 2/3. So let's just calculate that. I'm in degree mode. So second sine. And actually, if we have to put our answers in radian at the end anyways, I might just go to radian, save a step for later. Okay, so pardon me. Make sure you're in radian mode. And we're just going to go second sine square root of 2/3. Did you guys get 0.955? Did you even check it, Stan?
I trust you.
Well, thank you. Okay, so we've got to apply this value in quadrant 1, in quadrant 2, 3, and 4. And they're telling us just to round to the nearest tenth, so let's just go with 0.96. Okay, keep in mind with radian we have 0, pi, and 2 pi. So when we're calculating quadrant 2, we're going to go pi minus 0.96. In quadrant 3, we're going to go pi plus 0.96. And then quadrant 4, 2 pi minus 0.96. Okay, so let's just calculate those solutions. We get x equals 0.96. In quadrant 2, pi minus 0.96. We get 2.2. Nearest tenth, I put it to the hundredth.
Oh,
I guess, I don't, maybe I'll round at the very end then. Okay, so let's go pi minus that. So pi minus second sine square root of 2/3. Okay, so we got 2.186. If I round to the nearest tenth, I'm going to get 2.2. In quadrant 3, I'm going to go pi minus 0.955, 3166181. And I get, sorry, I got to add it. Do you guys want me to put this on the screen? We're okay? All right. 4.1. Okay, and then quadrant 4, 2 pi minus 0.955. 3166181. And we get 5.3. Okay, now 0.96, if I round to the nearest tenth, is actually 1.0. But I don't want to round too early in your answers. You want to keep the decimals till the very end. Okay, so from sine x equals the square root of 2/3, we end up with 4 solutions as well. These are all in radians, so would it make sense that my other solutions should be in radians too?
yeah.
Probably. Okay, so 45 degrees is pi over 4. 135 divided by 180. We got 3/4 of pi. 225 divided by 180. Pi over 4 pi. And 315 divided by 180. 7/4 pi. So these are the 8 solutions that we were counting on the graph before. Okay, here and here.